Okay, hopefully didn't put you to sleep with that first one. If I did, I hope you had a good nap. Anyway, the next section that we're looking at is section 3.7, which is the hypergeometric probability distribution. Now, well, you think there might be something new here. Really, there isn't. We've done the hypergeometric, we just didn't put a name on it at the time because we didn't have random variables yet to work with. So here's the idea here. We're working with a finite population. That population size is capital N. We choose a sample of size little n without replacement. Now, as far as this population is concerned, we're dividing it into two groups. As far as group 1 is concerned, group 1 is usually the group that contains the things that we're counting. Group 1 has R items in it, or R members. And hence group 2 has capital N minus R members. And what we're getting the probability of here, and the random variable that we're working with, x, is the number of items or members in the sample coming from group 1. Now, the thing you got to remember here is we're choosing items without replacement. So, as we've done in chapter 2 and a lot of other places, this is telling us that we're going to need to use combinations. So essentially, when you go back to section 2.6 and then things that we also did in 2.8 and to some extent in 2.9, we're using the combination formulas that we use there. So as far as this is concerned, get some space here. As far as P of x is concerned, remember, we're choosing a sample of little n items from a population of capital N items. So the number of ways we can do that is capital N choose little n. As far as the numerator is concerned, we've divided things up into two groups. One of the groups has R items in it. The other group has capital N minus R items in it. And like I said, we're interested in the probability that X of them come from group 1. And if they're X coming from group 1, then there must be little n minus X coming from group 2. Now, as far as the possible values of X are concerned, well, certainly we can start out with 0, 1, 2, and so on. But we have a maximum. But that maximum depends upon the set of numbers that we've got. Certainly, you can't have more items in your sample coming from group 1 than you have items in your sample. But similarly, we can't have more items in our sample from group 1 than there are items in group 1 to begin with. So as far as this is concerned, the largest possible value here is going to be the minimum of little n and R. The calculations you've seen before, but just as a reminder here, we'll go through a couple of them. Hopefully you've got your book with you. If not, hit pause, go get your book. Unless you're one of my friends from college watching this to mock me, in which case, why are you wasting your time? Anyway. Okay. So out of the book here, this is problem 3.102. We're going to do both 102 and 103 on page 128. First one's one of those standard earn problems. Apparently at one point or another, people who ran mausoleums must have been into probability to have all these urns. I guess before they filled them with the ashes, this is what they were doing. So anyway, this one says, an urn contains 10 marbles, of which 5 are green, 2 are blue, and 3 are red. 3 marbles would be drawn from the urn, one at a time, without replacement. What is the probability that all 3 marbles will be green? Well, as far as we're concerned here, for this problem, even though there are 3 colors, we've really divided this up into green and not green. We're told that 5 of the marbles in the urn are green, so we know that R is 5. We also know that there are 10 marbles in the urn, so capital N is 10, and hence the number of not green marbles would be cap N minus R, which is also 5. We're also told that we draw 3 without replacement, so as far as this is concerned, little n is equal to 3. So at this point, if we were to look at the mass function for x, this would be 5 choose x. This 5 corresponds to the 5 for green. And then 5 here, choose 3 minus x. This 5 corresponds to not green. And then this is going to be divided by 10 choose 3. In this case, the sample size is larger than the group 1 size, so the only possible values for x will be 0 through 3. And in this case, we're interested in the probability that x is equal to 3. So I'm going to erase x here and substitute n. So we're looking for P of 3. We want all 3 marbles to come from the green batch. So we'll put those there. And hence we didn't choose any of the blues or yellows. That'll be a 0 there. You're using those same NCR functions on your calculator, although these numbers are small enough you can do those on your own. If you grind this out, it works out to be 10 over 120, or 1/12. Now, one area that the hypergeometric is used in is the notion of what's called acceptance sampling. And in acceptance sampling, what happens is that a company that buys a large group of products, it could be a company such as Dell when they go to buy chips from a company such as Intel, or it could be some large supermarket chain and they're buying loaves of bread, something like that. But basically what's going on here is that they can't inspect everything that they're going to buy. So there's this big batch of items that they're going to buy, and they go ahead and sample some of them, and then based upon how many items in their sample are defective, they make a probabilistic decision on whether or not they're going to purchase the lot, or basically tell the company, pack your stuff back up, go home, because there's just too much of a risk that we're going to have to take a bunch of returns and lose money. Okay. Well, that's kind of a lead into the next problem, although the next problem is a variation, a small variation. So in this one, it says a warehouse contains 10 printing machines, 4 of which are defective. So our population size is 10. It says a company selects 5 of the machines at random, thinking all are in working condition. What is the probability that all 5 of the machines are non-defective? So for our purpose here, we're calculating X, the number of non-defective machines. So because we're doing that, the value of R is 6. And 5 machines were chosen. So little n is going to be 5. And again, as far as the mass function is concerned, P of x is equal to 6 choose x times 4 choose 5 minus x divided by 10 choose 5. Again, the sample size is larger than the group 1 size, so x is bounded by the value of little n. X is 0 through 5. Again, in this problem, we're interested in the probability that all 5 are non-defective. So we're looking for P of 5. So this is going to be 6 choose 5. This is going to be 4 choose 5 minus 5, or 4 choose 0. 5 defective, 5 non-defective, and 0 defective. If you go ahead and do this calculation out, it's 6 divided by 252, which amounts to 1 in 42. Failed to mention, I changed problems here. So this problem with the defective machines, this is problem number 103. Next, we've got the mean and the variance. Unlike the other two that we've done already, the geometric and the binomial, we're not going to derive these. I'm just going to give them to you at this point. We're not going to go through the algebra of this one. It's also not part of your homework to do the algebra of this one. But here's what we've got for the formulas. The expected value of x is equal to little n times little r divided by cap n. And the variance of x is equal to little n times r over cap n times cap n minus r, all divided by cap n, times, I'm going to draw this with an arrow so I have enough room, times cap n minus little n divided by cap n minus 1. Sorry, I can't zoom back because the camera won't stay in focus if I try to back up too much, so we'll work with this. So we've got these formulas. We'll say some additional stuff about those formulas after we get through this example. The problem right now we're looking at is problem 106. It's on page 129. And it says to refer to exercise 103, so the problem we just did with the defective and non-defective machines. It says the company repairs the defective ones at a cost of $50 each. Find the mean variance of the total repair cost. So for our purposes, the first thing that we need to come up with would be the mean and variance of the number of defective machines. So plugging in our values for that problem, we have the expected value of x equals, well, we have a sample size of 5. In the population, there were 4 defectives. And remember, we're looking at defectives here, so we've switched what the value of r is. In the previous problem, we were actually calculating non-defectives. Here, we're looking at defectives. So that's why r is 4. And capital N is 10. That was our population size. For the variance of x, we've got 5 times 4 over 10 times 6 over 10 times 10 minus 5 divided by 10 minus 1. If we grind those out, turns out that the mean is 2, and the variance works out to be 2/3. So now going back to the problem, at 106, we said we've got a cost function here. So I'll leave this up so that you can see what we're doing here. Our cost function, C, is equal to 50 times x. And we want the mean and the variance of that cost function. So for the expected value of C, that's the expected value of 50x, which is equal to 50 times the expected value of x, which is 50 times 2. So our result here is $100. For the variance of x, or sorry, for the variance of C, that's the variance of 50x. Remember, according to our rules in sections 3.4 and 4.4, 3.3 and 4.3, whenever you pull a multiplicative constant outside the variance, you have to square it. So this is 2,500 times the variance of x. So that's going to be 2,500 times 2/3. And so what we end up with is 5,000 over 3. And remember here that the units are the units squared for the original measurement. So this is going to be dollars squared. Okay, so as far as the last piece of this is concerned for the hypergeometric, going back to formulas that we had for the mean and variance, expected value is equal to little n times r over n. We'll take a look at this piece first. What we're going to do, as far as this problem is concerned, is we're going to let capital N go to infinity. Okay, we're not talking about a truly infinite population, but just one that's huge, relatively. But we're also going to let r over n stay constant. So in other words, in the case of the defective machines, we had 10 machines, 4 of them were defective, so 40% of the machines were defective. We're letting n get very large, so say we had 100,000 of the machines, we would still keep the ratio of r over r to n to be 4 to 6, so that 40% of them would be defective. So as far as r over capital N is concerned, this is approaching a constant. and we'll call that constant defective rate in that example P. So as n goes to infinity and r over n goes to P, then the expected value of x is equal to n times P. You've seen that formula before. We'll come back to it in a moment after we do the variance. We'll do the variance here, put the result up here. So for the variance of x, I said n times r over capital N times n minus r over capital N times capital N minus little n over capital N minus 1. So as far as this is concerned, under the same conditions, this is n, this is p. Recognize that n minus r, capital N minus r over capital N is just the same thing as 1 minus r over capital N. So in that limit notion, this becomes 1 minus p. For the last piece, go back to calculus 1. We're looking at this at the limit as cap n goes to infinity. So when you think about this problem, this part is a function of capital N. And so what we've got here is a rational function. The degrees of the numerator and the denominator are the same, namely 1 in this case. But as long as the degrees of the numerator and denominator are the same, then the limit of this term is, if you remember, the ratio of the leading coefficients. Well, the leading coefficients in both the numerator and the denominator are 1, so in the limit, that becomes 1. And remember that 1 minus p is q, so in the limit, the variance of x becomes n times p times q. Hopefully you figured it out before this, but if you didn't, you recognize here that the mean and the variance under these limiting conditions become the mean and the variance for a binomial distribution. So what we're saying here is that the hypergeometric, when you have a very large population, can be used to can be approximated by the binomial. And you say, well, how do you do that? Because with regard to the binomial, you're supposed to have the same probability of success on every single trial. And we're doing sampling without replacement here, so things are going to change. Well, the reason the approximation works well, let's say that you're looking at a million machines and 40% of them are defective. Well, if you take a group of 5 out of there, when you take the first one out, after the first one's gone, you either have 400,000 defective machines left divided by 999,999 machines left, and that's still very, very close to 0.4. Okay. So although the probability technically changes, the numbers are close enough that we can get an approximation. It's not going to be a perfect approximation, but in general, it works pretty well. And so when you ask, when can you use this? Generally, the approximation works well when your sample size divided by your population size is less than 0.05. So as long as you're not taking more than at least 5% of your population, the approximation will work relatively well. So let's go back to that notion with the defective machines. And let's just say we've got a huge warehouse here. The warehouse has got 1 million machines in it. $400,000 are defective. if you prefer a gambling example, then think about the casinos that are still playing blackjack with cards as opposed to computer-based blackjack. A lot of the casinos that play with the cards, they'll end up having a 25 deck stack or a 30 deck stack, because in a single deck stack, if you see 3 aces disappear and the dealer's got a king, you're pretty safe to bet that the dealer's not going to end up with blackjack, at least via the king-ace route. So it's the same type of idea here. So what we're going to do here is we're going to take a sample of 5 of these. And our question here is, what's the probability that we end up having one defective? So, if we're using the hypergeometric, this is going to be the exact probability. P of 1 is going to be 400,000, choose 1, times 600,000, choose 4, all divided by 1,000,000, choose 5. I'm going to leave the punching into your calculator for you to do so you can compare the numbers. Gotta give you a little work while I'm out. Anyway, so that's the hypergeometric version. The binomial approximation, we've got n equals 5, and the ratio here, the fraction here is 400,000 divided by 1,000,000. So for this, we'll use p equals 0.4. And so we'll do the approximated probability, p of 1 as being 5 choose 1 times 0.4 to the first times 0.6 to the fourth. Like I said, punch those into your calculator, verify that they're very close, and they are, and you can see how the binomial can do this. In the original problem, where we had only 10 machines, if we were to do this, then the approximation would not work out well. So again, you want to be working with a large population size, and again, you also want to work with a sample size that's less than 5% of your overall population. The smaller that percentage is, the better the approximation is going to work. That's the end of the material for the hypergeometric. The one remaining video will be on the Poisson.